and we are almost done for the semester. We've had to adapt, and I'm going to try to summarize what you'll need to know for the final exam and try to help you get focused on prepping for that. Final presentation we went over in class, and I'm going to represent this model. And in this model, what I like to do is convince everyone that you got into kinesiology because you're interested or were interested in some way, shape, or form in performance. Performance is just how well you do something. And you may have gotten involved with kinesiology because you wanted to run faster or bike faster or swim faster, or maybe you wanted to be able to run longer and do a marathon or an ultra, something like that. Or maybe you got into kinesiology because you had an injury and you wanted to learn how to prevent future injuries, or maybe how to rehabilitate from an injury. Or maybe you know someone who is in cardiac rehabilitation. You wanted to be able to help people with heart problems recover from that. Or maybe you want to learn how to teach someone to do a particular motor skill, or coach, or do some type of personal training. Those are all great reasons to get involved in kinesiology. But at the end of the day, you're all interested in how well we do something, and that's performance. Now, from a very basic perspective, performance is nothing more than a bunch of movements put together. Okay, a bunch of movements put together from a mechanical perspective. And in that perspective, we need to know things from anatomical kinesiology, and you learn movements and structures in A&P and in KIN 245, anatomical kinesiology. And you learn terms like flexions, extension, rotations, internal rotations, external rotations, circumduction, what have you. Those are all important terms to know and use as we continue to go forward in our experience of kinesiology. In these classes, you would have learned about concentric and eccentric and isometric contraction, and we've talked about those in this class as well. What we really added to this part here was relative angle and absolute angle as a way to represent angular position. And remember, relative angle is a way to represent two segments relative to each other. So elbow, shoulder, knee, hip, any joint angle is a relative angle. And then absolute angle or segment angle is the way to represent a segment's orientation in space. So segments like thigh, leg, trunk, arm, those are all segments. And we represent those segment angles by drawing out a reference line and then taking the angle between that reference line and the segment of interest. So you should know the similarities and differences between relative and absolute angles going into the final. Okay, now what are movements? Well, again, from a very physics perspective, movements are nothing more than displacement, a change in position over time. And when we are studying displacements in time, we are really in the branch of mechanics called kinematics, the study of movement, regardless of the forces causing those movements. And we went through three types of movements: linear, angular, and general. All points of an object travel the same distance in linear movement. All points of an object travel about an axis of rotation for angular movement. And then general is the combination of linear and angular movement. And we went through three main categories of kinematic parameters: position, velocity, and acceleration, both for the linear world and the angular world. And we do one analysis at a time. For position, we also broke that down into two really important terms: distance, total change in position, and displacement, straight line distance between 2 points. And we used the equation delta S equals SF minus SI, final minus initial position. Or from the angular world, we use delta theta is final angular position minus initial angular position. Then we used velocity which is the rate of change of position, is the general term. More specifically, rate of change of displacement. And that we used in the linear world, V equals delta S over delta T. For position, we're used any units of length, so meters, feet, yards, anything like that. For velocity, we used units of displacement over time, so meters per second, yards per minute, feet per second, miles per hour. All those are units for velocity. And we know that speed, we used distance over time, or if you're in physics, we would say speed is the magnitude of the velocity vector. If we're in the angular world, we use omega equals the angular displacement, delta theta, over time, delta t. And there we would use units of degrees per second, radians per second, revolutions per minute, things like that. And I should have mentioned up here, for angular position, we can use units of degrees, radians, or revolutions. Any of those are fine. Our next kinematic parameter is acceleration, time rate of change of velocity. And we use the equation A equals delta V over delta T, which is delta V, change in velocity over change in time. That's the linear equation. In the angular equation, we used alpha equals delta omega over delta T. Final angular velocity minus initial velocity divided by the change in time. And so you need to know these 6 equations, and you need to know the unit for each of these parameters. And remember, here in the angular world, using degrees per second squared are fine, or radians per second squared are fine. Later on, when we get to torque, we know we need to use radians as our base set of units for angular parameters. Okay, so displacements in time cause some movements. We put names on those movements. We have some descriptors of those movements. We have ways to represent those movements. And those movements put together in a particular way result in a performance. I need flexion and extension during running, what have you. All right, so what causes the displacements? Well, we have kinetics. We have kinetics. We have forces, a push or a pull that tends to cause movement, cause a displacement in time. And when we start looking at forces, we're in the branch of mechanics called kinetics, study of forces causing movement. And we took a Newtonian approach, so we need to know Newton's laws of motion. Oh, sorry, I forgot this part over here. And for kinematics, we looked at kinematics graphically by graphing position versus time, velocity versus time, and acceleration versus time. And we looked at the math behind the relationships of these 3 parameters. Velocity being rate of change of position, which also is represented by the slope of the position versus time plot, and acceleration, which is rate of change of velocity, which is represented by the slope of the velocity versus time plot. And we used phrases like speeding up, moving in a particular direction, slowing down, and moving in a particular direction. And so those you should be familiar with, and I've got a video on those relationships. Okay, sorry, back to kinetics. We have Newton's laws of motion, inertia, which is a law of inertia, which is an object will continue in its state of motion unless something causes a change in that motion. So that's an observation. Newton's second law is when a force acts on an object, it will cause a change in motion using this equation. We add up all the forces acting on the object, and we can understand the product of mass times acceleration. Mass is a measure of an object's inertia, units of kilograms, and that inertia is an object's resistance to change motion, and that's in a linear world. And in the angular world, we used T equals FD perpendicular, which is the way we calculate the tendency of a force to cause rotation, and we need to know 2 things: the magnitude of force and the moment arm of that force. And we actually spent quite a bit of time going through how to graphically understand the moment arm when when a force is being applied to a lever. And we also did types of levers, and um, we did 3 classes of levers. To understand the kinematics of an object rotating, we use this equation. Sum of torques acting about an axis of rotation is equal to the product of moment of inertia and angular acceleration. Here, for the angular acceleration, as I mentioned over here, we need to use radians per second squared. And moment of inertia has its own equation. We add up all the mass of an object and how far that mass is from an axis of rotation squared. And you should be able to distinguish between moment of inertia and inertia. Okay, so our angular parameters versus our linear parameters. But you can see the parallel between this equation, sum of torques equals I alpha, and this equation, sum of forces equals MA. All right, and so this is all has to do with Newton's laws of motion. And then the last law of motion is action-reaction, which is really any force created by an object, there is an equal and opposite force acting on the object. And the importance of this law is when we do a kinetic analysis, we only identify the forces acting on the object to understand the acceleration of the object. But we often have to do this mental gymnastics between, well, we're really interested in the forces created by a person, but we're really, to do a kinetic analysis, we identify forces acting on the person, not by the person. And I just put these equations down here. These are just different forms of this equation. Sum of forces acting on the object equals MA, and sum of torques equals I alpha. And here we look at this a little differently. We look at impulse causes a change in momentum. Momentum is mass times velocity, and an impulse will cause a change in mass times velocity, so change in momentum. And same thing in the angular world, we have angular impulse causes a change in angular momentum. Angular momentum being the product of moment of inertia and angular velocity. And so these are 2 different forms of the equation, and they just help us understand some movement strategies in terms of landing from a jump. We may reduce the amount of force by increasing the delta T, or how long that force is being applied, to change the momentum of an object. Or if we're doing aerial maneuvers, which is what I covered in another video, we know that once we're off in the air, that the angular impulse there's no change in angular momentum. So this angular impulse, or the angular momentum, is constant because there's no additional torques acting on the system during flight. And so this ends up being a 0 on the left-hand side of the equality sign. So that means that angular momentum is constant at the moment the person becomes airborne. And we had I went through that in a separate video. Okay, so that's our kinetics, study of forces causing movement. So where do forces come from? Well, they come from external to the body. So ground reaction force, gravity, for example, those are examples, so e.g. And we have internal forces, muscles, tendons, bone on bone, and what have you. And this is the part that we really didn't get to too much this semester, but some of that you get from exercise physiology. A lot of it you actually get from exercise physiology. And in exercise physiology, you really talk about converting chemical energy to mechanical energy. And this is the part that we did not get to as much during this semester in looking at mechanical energy. All right. But that's in essence what your body's doing, is you're taking chemical energy, your fats, glucose, proteins even, and you're converting that chemical energy to mechanical energy. And that mechanical energy ends up causing movement. And there's terms like aerobic power and anaerobic power. This power is how fast we're converting chemical energy to mechanical energy. And I'm not going to emphasize this in the final. But if you take a class like 457, physiology of endurance performance, we actually spend more time on these parameters in that class. All right, so how do muscles know what to do? Well, we have the central nervous system that is telling muscles what to do. Those muscles are generating forces. Those forces are causing a displacement in time, and those displacements in time create a movement. We put a name to those movements. Those movements put together in a particular way end up being a performance, which is why I say we're all interested in human performance when we're taking a class like this. And I put environment up here because environment can influence what the brain is doing. And we talked about that in the beginning of the class with the pressure of performing in front of a crowd or what have you. And if we send the wrong signals to a muscle and the muscles generate the wrong amount of force or in the wrong amount of applied at the wrong amount of time, then that's going to create the wrong displacement or a wrong displacement in a period of time. That's going to create the wrong movement, and that's going to create an error in performance. So all these things go together with trying to understand human performance. Our focus this semester was really on kinetics and kinematics and some information about setting up reference frames or descriptors of human movement as well. Okay, I hope this is helpful as you look in this semester. This was all done in 15 weeks. And it's a little odd with the COVID-19 because we had to adjust about halfway, 2/3 through the semester. And hopefully you were still able to get some good information out of the videos that I posted. I'll post some more material on Web Campus in addition to this, and please email me or message me if you have any questions going into the final. All right, thanks everybody.